Hello everyone, today let's do the Monty Hall problem, quantipus number 97. So you're a contestant on a game show and there are 3 closed doors. Behind one is a car and behind each of the other 2 is a goat. So in the game show what happens is I pick a door, let's just say it's door C. Then the host, who knows what's behind every door, opens one of the doors I didn't pick, so he's either going to open A or B. And what he reveals will always be one of the goats. So let's just say in this example he revealed door B and it's a goat. And now it gives us the option to switch to door A to try and find the car, or we can stay with door C. So which option gives us the higher chance of winning? You'd think that it's equal, but it's actually not. So essentially what we need to find is the probability that the car is behind our chosen door C, right? We chose this door given that the host revealed a goat at door B. So you would think that this would be 50%, but it's not. And the reason for that is that the host reveals the goat and he knows what's behind every door, so he has more information than you. So it's not like he's just randomly choosing which door to reveal, he's always going to choose a door with a goat behind it to reveal. So you can understand that this is a different situation than if I just went up to door B and opened it and it just happened to be a goat. In that case, I'm just randomly sampling, and then the odds of goat behind either of the other doors would be 1/2. But the key difference here is that it is the host revealing the door and it's not randomly sampled. All right, so let's just actually come down and solve the problem, and then it will make a little bit more sense. All right, here's my sample space partitioned into thirds because the car could be behind any of the 3 doors with equal probability. So now let's figure out how our sample space gets restricted when H happens, right? We need to find for this the probability of C intersection H divided by the probability of H. So we have a partition of our sample space. We have some event H that resides in this sample space. Let's just say maybe it'll look something like this. So since A, B, and C are disjoint and collectively exhaustive, we know law of total probability, the probability of H is just going to be equal to the sum of the intersection between H and all of our sets A, B, and C. Okay, so that's just law of total probability. What does it mean visually? Well, H can just be broken up into these parts and then summed up, the intersection with A denoted by that blue part, and the intersection with B, the red part, and the intersection with C, this orange part. So now let's go through and calculate all of these individual parts. So obviously my prior for A is going to be 1/3 because the car originally could have been behind any of the 3 doors. So now we ask ourselves, if the car actually was behind door A, then what would be the probability that the host reveals a goat behind door B? Well, if I pick door C and the car is behind door A, the host has to show a goat and he can't show the door that I picked, right? So he has to show door B. So the probability that the host reveals door B, given that the car was behind door A, is equal to 100%. Okay, so boom, we just calculated the probability of intersection between A and H, because obviously this is just equal to the probability of H given A times the probability of A. Okay, now let's calculate the intersection between B and H. So let's imagine first that the car is behind door B and the other 2 are goats. So what's the probability that the host reveals the goat behind door B, given that the car's behind door B? Well, this is obviously 0%. The host cannot reveal a goat behind door B if there's a car behind there. So this, which was equal to this times the prior, which is the probability of B, which also would have been 1/3, is going to be a term of 0. And now let's look at the intersection C with H. We already know how we're going to calculate this. We're going to take the probability of H given C times the prior, the probability of C, which we already know is 1/3. So what's the probability he reveals door B as a goat, given that the car is behind door C? So now door A and door B both have goats behind them, so the host could have chosen either door to reveal as the goat. So this is going to be 1/2, right? This is 50% odds that he chose door B out of the 2 doors. All right, so we now have all the terms for our equation, so let's just plug everything in. The intersection of C with H was 1/2 times 1/3, which is going to give us 1/6 on the top. And then we need to add the sum of these on the bottom. So the intersection with A was equal to 1/3, and then the intersection with C was equal to 1/6. So 1/3 plus 1/6 down here. And this is just equal to 1/6 on 1/2, which is equal to 1/3. So this is the probability that the goat is actually behind door C, given that the host revealed door B. And the probability that the car would have been behind the door that you didn't choose, the one that you could switch into, given that he revealed door B. Well, that's just going to be equal to 1 minus this, or you could just plug in 1/3 on 1/3 plus 1/6, which is 1/2, which is equal to 2/3. So therefore you should switch because your odds of winning the car are higher than if you stay. So what would the green bubble actually look like drawn to scale now? Well, for A, the probability of H given A was equal to 100%, so this will occupy 100% of A's mass. And the probability of H given B was 0, so it'll occupy 0% of B's mass. And the probability of H given C was 1/2, right? So this will occupy half of C's mass. So you can see that A's mass intersects with H double the amount that C's does, so the probability of A given H is going to be double that of C, which we got. Now instead, imagine the other scenario where I just sampled door B and it happened to have a goat behind it. Well, now the probability of A, given that B was randomly sampled and happened to have a goat behind it, is going to be 50%, because 50% of the time the car will be behind A, and the other 50% of the time the car will be behind C. Well, now you can see that the probability of A given this new event and C given this new event are exactly equal, so our probability would be 1/2, and we'd have an equal chance of winning whether we stayed or switched. But you can kind of understand how when the host reveals the door, it's not random sampling, right? He's forced to reveal a door with a goat behind it. So our answer is going to be different. And what is the probability of winning if you switch? Well, we found it was 2/3, and if you stay, it's 1/3, so you should switch.